Okay, this is the second part of your lecture for this video. Okay, this is now how we're going to use molality to calculate this freezing point depression and boiling point elevation. Okay, now the trick to these problems is you need to know your solute, and if you're getting more solute when it dissolves in water, and your solvent. Okay, the magnitudes of the freezing point depression, so delta, which is change in temperature for freezing, and the boiling point elevation, so change in temperature of boiling, is directly proportional to the molar concentration. So with that being said, if I have delta T of F, so how much is my temperature changing, it's going to be equal to molality, okay? But we have to add a constant as well, which we'll talk about here in a second, okay? So molality is going to be directly related, so they're going to be on opposite sides of my equation. And since I'm talking about F, or freezing, I'm going to have this thing called a constant, okay? And this is going to have to be given to me always, okay? So typically how these problems look is you're given enough information to solve for molality, and then you have to plug it into this equation to figure out how much your temperature is changing, okay? And you can do the same thing for temperature boiling. It's going to be equal to the molality times K boiling, and this will be a constant. And again, unless it wants you to solve for that value, it'll have to be given to you. Okay, so let's look at some problems here. So antifreeze protects a car from freezing. That's why it's in your car, okay? It also protects your car from overheating. Okay, so antifreeze uses this idea of colligative properties to keep your car at an okay temperature. Okay, so we're going to calculate the freezing point depression and the freezing point of a solution. Okay, so I'm ultimately calculating for freezing point depression. Okay, so this is going to be the delta TF that I'm trying to solve. And it wants my new freezing point of my solution. So this is going to be the new freezing point of the solution. Hopefully our solvent is water, because whatever our freezing point is, whatever our delta F is, we're going to subtract that from 0 because that's what water freezes at. Okay, so let's look. Let's keep reading. Of a solution containing 100 grams of ethylene glycol, antifreeze, and 500 grams of water, okay? And the KF of water is 1.86 degrees Celsius per molality, okay? So we're in water, so water is going to be our solvent. So we have 500 grams of H2O, and my solute is ethylene glycol, and I have 100 grams of C2H6O2. Okay, now here's the thing. This is a covalent molecule, meaning no metals. So it's not going to break into anything. So my number of solute particles is just going to be 1, because like I illustrated in your lecture before, your chemical reaction going from a solid to aqueous is just going to look like this. Okay? And I'll illustrate this a little bit more here in a minute. Okay, so that being said, I'm looking for delta T of F, and delta T of F is equal to the molality times that KF, okay? So I have KF, it was given to me, okay? So I have to solve for molality, so that's the first step. So molality is equal to moles of solute divided by kilograms of solvent. Okay, now here's the thing though. I'm not given moles of solute, I'm given grams of solute. So that's the first thing I'm going to have to do is convert into moles of solute. So I'm going to say question mark. Moles of C2H6O2 is equal to, and let's put a decimal here just so we can keep some sig figs, is equal to 100 grams of C2H6O2. So for every 1 mole, it's going to weigh, so I'm doing 12.01 times 2 plus 6 hydrogens plus 16 times 2, which is, so I get 62.08 grams. So that's going to go on the top. So I'm going to do 100 divided by 62.08. So I get 1.61 moles, so it's equal to 1.61 moles of my solute. And I'm dividing that by kilograms of my solvent. So I have to go 1, 2, 3. So it's going to be 0.500 kilograms of H2O. So my molality for this problem is 1.61 divided by 0.5 with 3 sig figs is going to be 3.22 molal. Okay? Now that I have molality, I can calculate for this delta T of F. Okay? So let's do that. Delta T of F is equal to the molality that I just calculated times the constant that was given to me. So I'm going to do 3.22 molal times my constant, which is 1.86 degrees Celsius per molal. Okay? So my delta T, so I'm going to do 3.22 times 1.86, and I get, with 3 significant figures, 5.99. Molal cancels, so this is degrees Celsius. Okay, so this is just delta T. Okay? The problem is asking for the freezing point. Okay? So delta T is how much I'm changing my temperature by. So if water freezes at 0 degrees Celsius, and my temperature is changing 5.99 degrees Celsius, my new freezing point of water with antifreeze in it is going to be negative 5.99 degrees Celsius. Okay, so when you have antifreeze in your car, okay, it's going to drop the temperature at which the water inside of your car freezes, and that allows us to drive in temperatures when you would think that your car would kind of lock up with ice. Okay, so thank you, antifreeze. Okay, let's look at another problem. Let's look at number 2. Number 2 says, I'm going the wrong way. What is the freezing point depression of an aqueous solution of 10 grams of calcium chloride? And I don't know why this is down here. Let's scratch this out. In 50 grams of water, and again, the KF of water is 1.86 degrees Celsius per molal. So again, our solute is dissolving, so our solute is always going to be the smaller value. So we have 10 grams of calcium chloride, okay, and the solvent is 50 grams of H2O. Okay, now this is what I'm talking about before. So calcium chloride is an ionic compound. So when it dissolves in water, you actually make calcium ions and chlorine ions, okay? But if I was to think of this like a chemical reaction, this is not balanced, right? Because I have 2 chlorines here and 1 here. So I need to put a 2 here to make it balanced. Now, this is the thing. When I figure out what my molality is, I'm going to have to multiply it by 3, okay? Because I have 3 values or 3 ions contributing to my temperature change, okay? So let's look at this here for a second. Okay, so we're going to do the same thing that we did before. So I'm going to calculate my moles of solute. So I'm going to say my molality, my molality is equal to moles of solute divided by kilograms of solvent. But again, I'm not given moles of solute. So I have to say, question mark, moles of calcium chloride is equal to, I'm given 10.0 grams of calcium chloride. So for every 1 mole of calcium chloride, it will weigh, so it's 40.08 plus 35.45 times 2. So it's 110.98. So the amount of moles that I have, 10 divided by 110.98, is going to be equal to 0.0901 moles. Okay? So that's what's going to go on top. So I have 0.0901 moles of calcium chloride. Oops, switch those. Divided by, I'm going 1, 2, 3, so it's going to be 0.05 0.50 kilograms of H2O. So my molality here is going to be 0.0900 divided by 0.05. My molality is going to be 1.80 molal. Okay? But the question is asking for the freezing point depression. Okay, this time I'm just doing delta T of F is equal to the molality times Kf. Now here's the thing, we have to add another value in here now, because instead of just having 1 like we did up there, I have 3 because I have 1 calcium and 2 chlorines. And that's called I. It's called the Van Hoft variable, and that's just going to indicate how many solute particles we have present. So we're going to do 1.80 molar times that 1.86 degrees Celsius per molar times 3, because I have 3 solute particles. So I'm going to do 1.80 times 1.86 times 3, and I get, changing the temperature, by 10.0 degrees Celsius. And calcium chloride is actually the salt that gets thrown on the roads, so you can see that it depresses the temperature by 10 degrees Celsius at that amount of solute and solvent. Okay, so that is freezing point depression. I bet you could figure out boiling point elevation. Okay, it's just the opposite of freezing point, meaning instead of subtracting from 0, after you solve for delta T of B, you're going to add it to 100. So for example, if I have delta T of B, it's asking for the boiling point, is going to be equal to the molality times the Kb constant times that Van Hoft if you're dealing with an ionic compound. So sodium chloride breaks down into sodium and chlorine, so Van Hoft is going to be 2. So this is going to be equal to 1.50 molal times 0.512 degrees Celsius per molal times 2, because I have 2 solute particles. So the boiling point elevation is going to be times 0.512 times 2 is going to be 1.54 degrees Celsius. So that means that sodium chloride increases the temperature of water boiling at 1.54. So my new boiling point is going to be 101.54 degrees Celsius, but with 3 significant figures, it would be 102 degrees Celsius. So that would be the new boiling point if you added salt to your water. Okay? Thanks for watching, guys. We'll do a couple more examples and tons of practice with this, but this is the last topic for this unit. Thank you.